Hello everyone, my name is Joris Peels, and this is another edition of 3D Printing News Unpeeled, brought to you by 3dprint.com. Today we're going to be talking about work by Abhishek Dand, Matthew Davidson, Hannah Zoltnik, and others at the University of Pennsylvania, the University of Colorado, and the NIST. And they are talking about additive manufacturing of highly entangled polymer networks in a paper that's published in Science, I think. And what they've been able to do is construct densely entangled long polymer chains out of monomers using two different processes. So one is a photoinitiator-driven process, and the other one is a redox type process. Both of those are light or polymerization processes, with the light polymerization being driven by the photoinitiators, which in this case they've used very little of, and then a dark polymerization process happening as well. And with that, they've been able to make DLP materials that may be useful for multiple material use, more functional type materials, and, well, perhaps significantly better performance in hydrogels and elastomeric materials, especially for like bioprinting, bio-use uses, maybe kind of like something like a wound dressing, or maybe a face mask for a burn victim or something like that. It could actually stick to a body. You could see how you could make like a conformal kind of thing for someone who's a burnt face to cover that really patch, and that might be able to heal them. Stuff like that. They call the process clear, it's something that could really be a pathway to specifically more elastomeric type things, or it could also just be a different way of getting a higher performance from DLPs or VAT polymerization type materials than the process we see now, which rely on different chemistries or rely on like a heat-driven process as the second kind of step. So the next news is that we are going to high-pressure phase transition in 3D printed nanolamellar high-entropy alloys by imaging and simulation insights. Now, this is a paper that's by Andrew Pope, Wen Chen, Hangman Chen, Yogesh Vora, and others. A whole bunch of big U.S. institutes work in this, Department of Energy, the University of Massachusetts, University of California-Irvine, University of Notre Dame, that kind of thing. And they 3D printed a octetic high-entropy alloy. It is, well, the name of it is crazy. It doesn't even have like some kind of like machine or human readable kind of name. I don't know what they call it internally, but it's like what is it? Nickel 40, copper 20, iron 10, chromium 10, aluminum 18, tungsten 2, or something like this. So really, we're talking really super exotic stuff here. And if it doesn't even have like a short form name, you're on that end of it. Now, what's exciting about this is that there's like this phase, this phase transition phase where a face-centered cubic and a body-centered cubic kind of phase initiates in this material. And that's done by very, very high pressure. What then happens is that if they see that there's this kind of alignment, and that alignment is so strong that it's actually really, really quite surprising. And actually it is, they subject it to 30 GPa of pressure, and it seemed to still be kind of in alignment and still be very strong and still kind of be able to function as a material. So that could be a new way of, let's say, designing, creating, or at least testing and finding new materials that could be incredibly strong and incredibly useful for space or applications, or things like oil and gas, or things underwater, or whatever. A lot of things like that. So I think that's really a wonderful thing. And the next thing is that a whole bunch of different companies, up to 57 different companies, got a part of a contract that totals $970 million, and it goes to 67 different companies, and that contract comes from the Rapid Sustainment Office. So the contract runs over 9 years, and it has to do with the rapid sustainment of the Air Force. The RSO is the rapid sustainment arm of the Air Force, and they want to, of course, keep their airplanes in the sky. They want to repair them as quickly as possible, have them right repairs so they don't get additional problems. They want to have availability of spare parts, and of course 3D printing plays a role in this. So this is a really, really big thing. This part of this this whole kind of contract is 3D printing, and part of it is a lot of other different things: scaling technologies, robotics, composites, all this kind of stuff. But does tend to give a lot of money to different companies. So Speed 3D gets some money, Authentize gets some money, Ascension gets money, 3D Systems does. So it's kind of like they're kind of trying to stimulate a bunch of companies to take part of this contract and to do things for sustainment. This is a huge opportunity, and there will be significant other opportunities like this in Marine Corps aviation, in for the military, for the Army, and for other types of branches of the military, other parts. So this is something that I think can grow and can really, really be significant for all of us. Well, thank you very much for your time. My name is Joris Peels, and have a great day.